Hello, everyone. Thank you for joining us today. My name is Jeffrey, and I will be your host for today's webinar on real-time interference-free virtualization with Zynq UltraScale MPSoC. Today's presentation is scheduled to last roughly 45 minutes with 15 minutes or so at the end for Q&A. Please type any questions you may have in the Q&A section on your left-hand side, and we will do our best to answer you at the end of the webinar. Now, before we begin, here are just a couple tips about the interface. To enlarge any individual window, click or tap on the square in the top right of the box. You might have to do that with the media player later in this webinar, as we will be doing a live demo. If you are having trouble with your audio, you may need to adjust either your device's volume or the volume in the media player that you can find on the left-hand side. The bar below contains a green icon that reveals our resource list with a PDF copy of today's slides as well as links so you can learn more about this project. This webinar will be made available for on-demand viewing later today at xilinx.com/webinars. You can also find it via the link that brought you here. And with all that housekeeping out of the way, I'd like to introduce our speakers. We have Giulio Corradi and Stefano Stabolelli here from Xilinx to speak about this project that was developed in part with Università Modena in Europe. So with that, I would like to go ahead and throw it over to Giulio to begin the presentation.
Thank you, Jeffrey. I really appreciate all of you taking time to join me and Stefano for the talk on mixed criticality and virtualization. It is a topic that we are very passionate about, and we are going to talk different topics. And over the next hour, Stefano and I will talk about predictability, mixed criticality, multi-cores, heterogeneous architecture, worst-case execution time, hypervisor, cache coloring, and in the context of mixed criticality for industrial, avionics, and automotive embedded systems. I hope that this talk you will have a better understanding of how Xilinx technology and Zynq UltraScale multiprocessor system-in-chip can solve some of your challenges when you transition from a single processor execution model into a multi-core and many-core, maintaining a predictability, as I said before, space and time separation, and reducing or eliminating interference between cores when using all the shared resources. We start with an example of mixed criticality in industrial automation. Typically, in industrial automation, you might have a high-performance single-core CPU that is implementing a PLC, so a programmable logic controller. The application might run in a multitasking system. You might have HMI, and in general, it's driven by a real-time operating system. On the similar elements, you might have also drives, and they have similar structures with an RTOS, with a motion control, a motor control. They have a very tight requirements in terms of real-time. They might use DSPs, and they might run in a combination of a single CPU plus a DSP. Then in the same environment, you might find a safety logic, a safety system that might be implemented with a couple of CPU, in general for redundancy and to provide the proper safety level according to the ISO 26262 for automotive and the IEC 61508 for industrial and other sub-norms. Everything today is going to be integrated into a single hardware unit with the multi-core, and so there might be some problems in terms of separations and real-time requirements. Similarly, in avionics, the mixed criticality is becoming extremely important. All the new aircraft are asking for additional functionality. Systems should be certified according to safety norms and safety standards. The systems are becoming very integrated, so what is called the integrated modular avionics, in a way that more and more electronics is packaged into a single chip. And there are additional applications that are asking for specific capabilities like very hard real-time requirements as well as a clear separation. In automotive, we have a similar concept. The mixed criticality is also there. Look into the autonomous drive today. That is a very advanced applications or the advanced driver assistance, as well as, I would say, other applications like infotainment. All those things have similar, I would say, requirements as in the industrial world and the avionics world. Some of them are safety critical oriented. Some others are just best effort, but they do have a very high computing demand. And them all need to be integrated into a single chip or a system on chip in general. So everything, all the different domains, I would say, they have a very similar requirement. If we go into multi-cores, is probably the common denominator is that there is a need of managing several elements. In particular, I would say I'm going through Zynq UltraScale right now to show how the multi-core, and in this particular case, is a heterogeneous system that is organized. There is an application processing unit that is a quad-core ARM Cortex-A 53 that is very capable. It's a 64-bit processor. There is a real-time processing unit that is a dual-core ARM Cortex R5 that could run in a split mode or in a lockstep mode for safety application. There are a certain number of, let's say, standard peripherals and high-speed peripherals and GPU over there. So it's a very powerful system on chip. And there is a programmable logic. The programmable logic could be used to tailor the application, taking advantage of, for example, hardware offloading, hardware acceleration, or to connect the system together in order to provide additional expansions. There are a significant amount of DSPs and memories and logic cells, so you can basically shape and morph your application at your needs. So that is the typical, I would say, system on chip plus a programmable logic. Let's see what is going to happen. In general, the applications are coming from a set of legacy applications. So you might have, for example, as I said, in the industrial case, for example, the PLC application that runs with a time span of, let's say, a millisecond up to 100 milliseconds. You might have a motor control and a motion control application that runs in 10 microseconds and 10 milliseconds at a time base. And you might have field bus applications that are running a little bit slower, let's say in the range of several milliseconds up to 100 milliseconds. And those are basically the legacy application, all those applications that need to be ported into the new environment. And in the past, previously, they made use of all the performance that the single processor was basically capable to deliver. Then there are new applications that are going to be very critical, for example, IoT gateway, in which you are going to expose your system in a mixture of communication as well as, say, control. And you might have, for example, some users applications. So because you have a multi-core, several processors that are available, you might need, for example, to make available one of the processors or more than one to your customer applications, and for that reason, the customer application should not interfere with the legacy application. And you might have also machine learning or artificial intelligence applications that are going to run in the system, in the programmable logic or in a mixture. So there are many things that need to be coordinated together. And that is imposing a particular restriction because, first of all, you need to partition the application. Second point, you need to identify within the proper partition how the performance are going to be achieved. And third point, you need to minimize the interferences that might be, let's say, performance interferences, or might be security interferences, or might be safety interferences. Those things, they need to be somewhat managed. And typically, there are a couple of approaches, and amongst those approaches, virtualization is one of them. So the typical goals are using the virtualization in order to maintain within the real-time cores the proper separation and having processes that are communicating with the real-time core. But the virtualization is running on the application core. And in particular, the virtualization allows you to create specific partitions. in a way that the critical domains are properly assigned. You might have a sort of static assignment, so every element in those partitions are allocated. You have the proper time separation. You have the space isolation because you might decide to run certain things on a particular CPU, and you don't want to create interference. And inside such domains, you have different criticality. So systems that are not able to tolerate, for example, interrupt latency, a system that can tolerate a little bit of interrupt latency, and systems that are basically best effort. So in this particular circumstance, let's look what is today available. So virtual machines and containers. Those are the mechanisms to virtualize the system. So the difference between the virtual machines and the containers, because normally are elements that are really, sometimes are really source of confusion, is basically that the virtual machines, it's basically capable to run several operating systems on a specific hardware, virtualizing the hardware itself. Instead, the container is going to virtualize the operating system itself. So in an embedded system, I would say both technologies are very, very useful, but the virtual machines are preferred when you need to support a rich OS, here is named guest OS, a real-time OS, and maybe a Baremetal application. And because often you don't have the ability to refactor the application, so you would like just to run the application as it is. But also you need, for example, safety and security, very strong safety and security separations. And the hypervisor in general that is responsible for managing the virtual machines is capable to work at a different level of privilege compared, I would say, to the operating system. So the virtual machines, beyond providing a full isolation, because every domain is not capable to see, cannot see any other resource of the other domain, you can map physical cores one-to-one into with a specific, I would say, OS. The containers are very useful for packaging applications that are running into a rich OS, for example, under Linux, and to provide the proper isolation. But you have a dependency on the operating system. So the container is basically a better choice when your high priority is maximizing the number of applications, for example, running independent IoT elements. And in general, I would say many applications are taking advantage of both elements. So there is a virtual machine manager, so there is a hypervisor, and it is managing the virtual machines. And inside one of these virtual machines, there is a guest OS that supports a container engine, so that the container is definitely the key elements here, and the container is then responsible to manage the different applications that could come in a packaged form, while maintaining with their hypervisor the other, I would say, the AUTOSAR in different core, or a Baremetal application in another core. Often this type of configuration makes also the safety analysis very much simplified, and that is an additional advantage. So using container and hypervisor is in general the way to go. But any time you start to share elements with a multi-core system, and in this particular slide there is an example, so low criticality that is running within the Linux with the container engine. You have an HMI, you might have a machine learning application, while the RTOS is running a PLC or a motion control system. And sometimes you have a Baremetal application running the motor control, so the inner loop of the motion control, and maybe a safety loop. I'm not talking about the real-time core that is normally used for other operations, but in this particular circumstance, the different cores in the multi-core, they share the level 2 cache. And the level 2 cache might be the source of issue, and in particular the source of issue that we are talking today. In general, I would say the level 2 cache, or the last level cache, if you have a higher number of cache levels, is shared. So it might be possible that one system, for example Linux, using a lot of cache and evicting maybe the AUTOSAR application that is normally executed with a time base. And this time base can be, let's say, several milliseconds, for example, 10, 20, 60 milliseconds, while the overall system might exhibit a sort of usage of the cache, so the cache is not used during this time frame, and the other processors could take advantage of this unused cache and trying to evict the cache. This creates a couple of things. The predictability is compromised, and then you have a very high interrupt latency. That is the topic of today, I would say. In general, in this particular configuration, the primary interfaces are the following. In the hypervisor is challenged because of the last level cache, and in general, any code that is larger than the level 1 cache is a sort of a target for eviction. So until you stay within the level 1 cache, everything goes fine. As soon as you exceed this value, the last level cache is going to be evicted. So there are a couple of solutions. One is a cache lockdown, but that is in general in the latest processing system, including the Zynq UltraScale, is not available. And the other one is the cache coloring. So it's a mechanism to create basically partition inside the cache and in the memory. So for the people that do not know how the cache works, normally the cache is organized in several elements. So you call it basically cache lines. And those cache lines consist on 64 bytes of memory that are getting loaded in a burst, and then the information is cached, basically is available in this high-performance memory. The cache memory is limited, as we know, it's 1 megabyte in the case of Zynq UltraScale, and several of those locations are going to be basically evicted. The process of replacing one cache line into another cache line is called, as I said before, eviction or cache trashing, and that is the problem we are talking about. The level 2 cache in Zynq UltraScale is basically divided in 16 chunks that are called ways. Every square in this picture represents one cache line of 64 bits. So in order to see where a specific cache line is need to be stored, the cache control divides the address in 3 parts. There is an offset that defines basically a byte within a cache line with 64 bytes of cache line, so there are 6 address bits. There is a set index that defines the cache line where the cache line is going to be stored. And so there are basically 1,024 sets, so there is a 10-bit address. And the rest of the address is forming a unique tag. That's how the cache works. The cache coloring is a software technique that is allowing cache partitioning without hardware support. The key concept here is the fragmentation of the memory space into a set of color, we call color. They have a very important property. The address are mapped into, let's say, different cache partitions. So technically, I would say the memory space, the complete memory space, is first divided into a number of sequential regions. So you see, in our case, with 1 gigabyte of memory, is divided in around, let's say, a little bit more than 16,000 regions. And then every region is then divided into a number of sequential subcolor that are, you see, C0, C1, C2, that are basically sized in function of the way size. So taking the way size and the page size and taking basically the size of the level 2 cache, it's possible to derive the number of colors. And in this particular, say, case, with the Zynq UltraScale, we have 16 colors. Then Stefano later on will give you additional details on that. So now my introduction is basically completed, and I would hand over to Stefano for the next part. Stefano, is all you.
Thank you, Giulio. Let me start by introducing Xen. Xen is a type 1 hypervisor. It's open source, has been around for more than 15 years now. It's a project under the Linux Foundation umbrella. It in many ways is structured like the Linux kernel in terms of how the contribution works, the license, or how many different vendors in different spaces work together to bring Xen to the masses. In terms of architecture, you see a diagram here on the left. So Xen is a type 1. That means it's higher privilege than anything else on the system, like especially like any operating system on the system. And they are running as virtual machine on top of Xen, including DOM0. DOM0 is the first OS that starts, typically Linux, and it's the one typically users interact with on the screen. Then from DOM0, you can start additional domains using command line tools such as Excel. It's also worth noting that Xen supports PP drivers. This is an infrastructure to share devices. So normally, all devices are automatically assigned to DOM0. So as you boot DOM0, DOM0 gets all your network cards, SATA controllers, GPUs, and so on. But it's always possible to directly assign these devices to other VMs. So you can take the network card and assign it to another VM. In addition, and that's where the PV drivers come in, especially for network and block, it's often very useful to share it across multiple VMs. You might want to share, to give a partition on your SD card to one VM and another partition to another VM. And PV drivers allow you to do that by allowing you to share a particular class of devices like block or network with multiple VMs. And we'll see a bit more later. But in terms of real-time and scheduling, really the most important thing is the kind of scheduler that you select to use. And then as a flexible scheduler architecture, where multiple schedulers are supported, and you can choose at runtime which one to use, or at boot time, either way. And you can do that with a command line parameter, sched equal with the name of the scheduler. Credit, the one below, is a default scheduler, the one typically used in the data centers, been in Xen for a very long time now. But if you and it allows you to have more virtual CPUs than physical CPUs, which is typical with the hypervisor. But really, if you care about low latency and real time, the best scheduler for you is not to have any scheduler at all. And in fact, we have an aptly named scheduler called null that, as the name suggests, does absolutely nothing. So what it does is simply statically assigns virtual CPUs, all virtual CPUs one at a time to physical CPUs until it runs out. Now, doing it this way, there is zero scheduler overhead, and the full core is dedicated to a virtual CPU. And that's really good to keep the latency low. But unfortunately, due to the cache issues that Giulio just described, it's still not quite enough, because through L2 cache interference, one core of one VM could end up affecting performance of another VM running on another core, so much so that it could even cause missed deadlines. So the solution, as Giulio went into a lot of details to explain, is to do cache coloring. And because we can't really, so cache coloring, the basic idea is, well, one VM is causing interference to another VM through cache lines, through the L2 cache. So why don't we prevent that by simply giving a subset of dedicated cache line to one VM and a different set of dedicated cache lines to another VM? If each VM has its own set of dedicated cache lines, then there is no interference. This is true, right? This basic idea is correct. However, it's not easy to be able to dedicate a set of cache lines, because there is no mechanism, at least in this generation of hardware, to just say, I want to divide the cache line into 4 subsets and give one to each VM. So instead, what we need to do is to really understand down to the details how the cache line get associated with memory addresses, and then allocate memory to virtual machine accordingly. So if we understand exactly how a memory address get associated with one cache line, then we can choose memory to give to VM in a way that the cache line, the related cache line, are always the one from the set we decided to allocate. So in the picture, let's say that we dedicate the blue cache lines to one VM, then we have to allocate the memory accordingly so that only the memory that has been marked as blue is given to the blue VM. And in short, and I'll give you more details in the next slide, but in short, you have to allocate one page every 16. So the trick is to allocate page 0, page 16, and so on to VM1, page 1, page 17, and so on to VM2. And that is what really gives you completely dedicated cache lines. So let's look at the Xen implementation. So the first thing we had to do in Xen was to really figure out the coloring allocation, how does it really work? And so all the calculation that Giulio explained, how the cache work, we had to do it in software so that at runtime we could make the right choices, do the right memory allocations. First thing, we had to detect the weight size. There are two ways we did it. So there is we added a Xen command line option so that you can add, specify by hand the weight size on the Xen command line. But it's also possible to automatically detect the weight size reading ARM registers. Once we figure out the weight size, which is on the Zynq MP is 64K, the next step is really to calculate the color bits mask. So 64K, it's order 16. However, so we have 16 bits to play with. However, we can only allocate memory at a page granularity level, right? We cannot really allocate less than one page. This is about memory mapping in the MMU, so they work at the page level. So the minimum is 4K. 4K is 12 bits. So 16 minus 12 give us 4. 4 bits. Those are the 4 critical bits with which we do all the coloring. So if you look on the screen, the color bit mask F000, those 4 bits, the F is really what determines the color. So if we apply that bit mask to any memory address, we can immediately figure out to what color it belongs to. So how many colors there are? That's quite simple. There are only 4 bits. So we have 16 colors. Also, dividing the total amount of memory by 16, we also can understand how much memory each color corresponds to. And each color corresponds to 256 megabytes. Next, now that we have we figure out the color bit mask and how to associate memory with color, the next step was to implement a memory allocator. So the default memory allocator in Xen is called Buddy, and is a classic algorithm. And for you guys that you studied computer science in university, you probably studied the Buddy algorithm. That's not what we used. So for this task, we needed a specialized algorithm that would really returns memory based on the color. So we added a second allocator. Second allocator, which we just called the colored allocator. What it does is it divides the memory pages into a list, one list per color. So on the Zynq MP, there will be 16 lists. Each list is just a simple linked list of pages from low to high addresses. So basically, it works like that. You need some memory, and you ask, can you please give me, I don't know, 2 pages of color 1? And then the allocator go from the linked list corresponding to color 1, and give you the 2 pages at the end. Or you could say, can you please give me 1 megabyte of color 1 or color 2? And then the memory allocator picks 1 megabyte worth of pages from either linked list 1 or linked list 2. So this allocator can be used for both domain memory, so the memory to allocate to virtual machines, as well as for Xen memory, so the memory used by the hypervisor itself. Everything I said so far was not trivial, but it wasn't that difficult either. So the real difficult part of this work, I would say, was Xen relocation. Now, to make this actually very solid and thorough, we also had to relocate Xen itself into colored memory, so that also Xen cannot be affected by this. And then by Xen, I mean the hypervisor code itself. So to do that, we had to copy the text of Xen at runtime to memory that was allocated using a given color, so striped memory, and then remap it contiguously in virtual addresses. That was not easy, and it took us a while to get it right. But now it's there and is in the Xilinx entry, and it works. OK, so now it's time to actually tell you how to play with this new technology, how to go and enable it and do your own test. So Xen, it's supported by Xilinx and is part of the Petalinux and the Octa releases. So you can just start off the Petalinux 2020.1 pre-built binaries. So you don't have to rebuild anything else. You can just take the Xen.fs, the Linux kernel, the device tree, everything from the 2020.1 pre-built binaries, except for the Xen hypervisor itself, because we want to rebuild that enabling cache coloring. Fortunately, rebuilding Xen is actually quite simple. Xen is very small, runs in EL2, so in hypervisor mode is completely separate and standalone. You don't need really any complicated setup to be able to rebuild Xen. You just need a cross-compiler like the one you can download from Linaro. You just need to set that your target architecture is ARM64, and then you are good to go. Like when you build the Linux kernel, you just set make menu config, you enable cache coloring across the architecture features, and then you type make. And you get the hypervisor with cache coloring enabled. How do you use it at runtime? OK, so that should be easy too. So the colors are from 0 to 15, because we have 16 colors. They are in terms of numbers. So the first things to set is the Xen and DOM0 colors. So if you look at the top part of the slide, the options for Xen and DOM0 are specified on the Xen command line. So typically on the that is on device tree. So you can just edit the device tree and add these options to the Xen command line. So the first option that you see there is the weight size setting. As I said, that can actually be automatically detected. So you don't actually need to specify the weight size. It's just there just to be, to give you all the options. If you run this inside QEMU, for instance, you'll have to specify it. But if you are running this on hardware, you don't need it. OK, Xen colors. That is the list of colors to be used by the Xen hypervisor itself. Because Xen is small and doesn't actually need a lot of memory, and one color, I'll remind you, is 256 megabytes, the color 0, so just one color, the first color, is more than enough for Xen. So University of Modena runs a lot of benchmarks and also tried to add more colors to Xen, and it doesn't really add a lot of benefit, because really Xen needs just one color. The next one, which is more interesting, is DOM0 colors. So DOM0 colors is the colors to be used for DOM0. And in this example, I put down 1 to 6. This is something to pay attention to. So I said a color corresponds to 256 megabytes of RAM, which is true. But the allocation is not done automatically. So there is still a separate option called DOM0 mem, has always been there, to specify how much memory to give to DOM0. So why keeping the memory allocation and color separate? Because this way, you have really maximum flexibility. you can use the same set of colors for two VMs that belongs to the same, conceptually the same real-time or the same safety environment. Or you could start two VMs with different colors, but just one shared color between the two to set up a shared ring, for instance. So either way, this way we don't tie the choice of your colors with the amount of memory necessarily. So that means that if you give them 0 colors, 1 to 6, you have up to 1.5 GB of RAM to give to them 0. So if you give 1 GB to them 0, all is good. But if you try to allocate 2 GB, obviously it's going to fail because it's going to run out of memory available in those colors, 1 to 6. DOM zero-less DOM use. So DOM zero-less is a relatively new feature in Xen you might not yet know about. So traditionally, Xen, as you saw in the earlier picture, will boot DOM zero, and then from DOM zero you have user space tools to start additional VMs. A couple of years ago, the first time was demoed, and then I think it went upstream last year. There is a new feature that allows you to boot multiple virtual machines in parallel directly from Xen. So you load the required binaries from U-boot, and then Xen will start DOM zero and additional VMs all at the same time on different colors. And that was mostly done to minimize boot times. So let's say in the picture you want to really minimize the boot time of the yellow VM. Now you don't have to wait for DOM zero to be fully booted. You just need to wait for Xen and yellow to be finished. So the configuration of these DOM zero-less VMs is done on device tree, and naturally the color is also chosen on device tree. So in this example, this is just a U-boot command to set the colors for a DOM-U called DOM-U0 to the color 7. Color 7 because this is a bit mask. So 0x80 correspond to color 7. And then for other DOM-Us, classic DOM-Us, the one that are started directly from Excel, you just select the colors as usual with just an option in the Excel config file. All right, so now I hope you got the gist of how to set up a system with cache coloring enabled. And I wanted to really show you what are the benefits of enabling cache coloring. And to do that, I'm going to show you benchmark results that were gathered by Marco and Luca from University of Modena. They ran a lot of samples, so we're talking about thousands of samples. And the configuration is really down below there on the slide. So Xen is using color 0 and 1. So I said that really only one color is needed. In this case, we gave 2 because we had colors to spare. Color 4 and 7 for the motor control DOM-U. So this is the environment during doing the latency measurements or measuring the time and so on. And then this is the Baremetal environment. So this is a tiny C application running in kernel space. It's not really an operating system. It's not even a kernel. It's trivial. Stress DOM-U. So each stress DOM-U and stress 2 DOM-U are 2 domains, also Baremetal application, that add stress on the cache. And what they do is really memcopy loops. It's just as simple as doing a memcopy in a loop. And we also had the same basically on Linux running in DOM zero and the stress command in the one below in the slide. And this is the first slide and also the most confusing for more than one reason. The first slide of results, I'm going to go into detail so that you're going to easily be able to understand all the following slides. So on the left, you see the latency in terms of nanoseconds. Lower is better, lower in more than one sense. So lower in terms of absolute numbers means better time, so lower times of execution or lower latency, but also the rectangle, the rectangle, the purple rectangle, the large one on the left, it's the variance of the results. So the smaller the rectangle, the more deterministic are the results, the more predictable are the results. So we want small rectangles and low on the y-axis. So this is also the most confusing slide for a different reason. This is a slide without interference, and is just measuring the time to run the motor control execution routine. Baremetal on its own, that's the result on the left. Baremetal on Xen without cache coloring, and that's the second column. And then the application on Xen with cache coloring enabled, and that's the third column. So again, the first one is Baremetal alone, and the second and the third are on Xen. As you might notice, on Xen is faster than Baremetal alone, which it's very counterintuitive and strange. Well, I have to tell you that sometimes when you enable virtualization, the CPU works in a slightly different mode. A new additional stage of translation is enabled. Things work slightly differently. So occasionally you see that actually some benchmarks are faster with a hypervisor than without a hypervisor. And I saw it in the past in previous iteration on x86 even, right? So it is surprising, but it's not unheard of. But the bottom line of this slide, I think what you should really focus on, is that the results are basically always below 2050. So let's say for simplicity, they are below 2000. So that is the key, results below 2000 nanoseconds. Now we added interference, so with a mem copy loop, as you remember, and the Baremetal results are really jumping up. They got worse. They are now above 6,000, approaching 8,000 nanoseconds. On Xen without cache coloring, it's still getting worse. Is approaching 8,000 nanoseconds. But when run on Xen with cache coloring enabled, that is the third column, the results are still lower than 2,000. So it's still unaffected. So we add another mem copy loop, increasing interference. Baremetal is getting worse. Xen without cache coloring is getting worse. But Xen with cache coloring enabled is still unaffected. And in the case of Xen, so the Baremetal results are the same, but in the case of Xen, we added even more interference in DOM 0. And now Xen without cache coloring is almost 12,000 nanoseconds, while Xen with cache coloring enabled is still below 2,000. So we plotted all the results together for your convenience. Basically, the two on the left are Xen without cache coloring and with cache coloring without interference, the one on the left. And then the one on the right, the two on the right are with interference, without cache coloring and with cache coloring. So as you can see from this summary slide, basically Xen with cache coloring is unaffected, almost entirely unaffected, while Xen without cache coloring, it goes significantly up, the execution times. Second benchmark might be even more interesting. That is the interrupt response time. It's basically a measure of latency. Latency, and is measured as the time when the interrupt fires minus the time when the interrupt was supposed to fire. So it's the difference between the time when the interrupt service routine runs and the time when the interrupt is set to fire. The timer is a timer in programmable logic, but you should be able to reproduce the results using the TTC timer or other timers as well. You should also note that as you try to reproduce these results, and this is true for the other benchmark as well, when we write benchmarks, and I speak for myself, but I think it's true for many people here, we tend to write small amount of code, like just what is enough to reproduce the issue. And that actually, in this case, is a problem, right? Because if you write a benchmark which is too small, what you end up is not seeing the problem because it's masked by the L1 cache. Right? The cache interference is on the L2. So if you just write the tiniest, the smallest possible benchmark, you might end up that the interference effects are masked by the L1 cache. So I recommend to add, this is a very rough way of solving the problem, but one way to solve the problem is by simply doing a cache flash once in a while in your measurement VM to flash away your L1 mappings. All right, getting to the results again. So this is the reference slide without interference. So in this case, things are as you might expect, in the sense that the Baremetal results are slightly lower than 500 nanoseconds, so certainly lower than the Xen results that are in the 2,500 and a bit more than that range. Why is it different? Well, in the interrupt path is actually different with Xen or without Xen. So in the normal case, the interrupt gets straight into the Baremetal application. In the Xen case, the interrupt is first delivered to Xen, and then Xen delivers a corresponding virtual interrupt into the Baremetal app running as a VM. So there is a longer code path to run. So let's have a look at what happens when you add interference. So because the starting point was so low, so it looks like the Baremetal application is fast, and it is fast, but in relative terms, it's actually got significantly worse. The second column is Xen without cache coloring, and that got definitely worse, and it's above 10,000 nanoseconds. So I'll remind you, from 2,500 to above 10,000. And the third column is the one with Xen cache coloring enabled, and is still unaffected at 2,500, around 2,500. So we add even more interference. The Baremetal application, again, not really visible here, but it gets worse. Xen with cache coloring disabled, so without cache coloring, get worse still. So here we are almost as 15,000 nanoseconds. Xen with cache coloring enabled, it's still the same at 2,500. And yet again, more interference. I don't have the number for Baremetal in this case, so just look at the Xen columns. Xen without cache coloring goes to certain results above 20,000, so from 2,500 to 20,000. But Xen with cache coloring is still around 2,500 nanoseconds. And now here on this slide, you see all the results together for your convenience. And basically what you should look at is the rectangle, the larger rectangle high above 10,000 nanoseconds. The three big rectangles are the results on Xen without cache coloring, while the results on Xen with cache coloring are down below, all stable at slightly more than 2,500 nanoseconds. All right, so I want to add a couple of more details on this before I move to the demo. PV drivers, as I mentioned, are a way to share your devices across multiple guests. So for instance, to share the network card across multiple guests. PV drivers, as of today, do not work with cache coloring enabled. I'm saying this to warn you if you're going to try this technology, but also as a positive note, because we are actually actively working on fixing this. And we should be able to solve to make it work to enable PV drivers with cache coloring in the early part of next year. So the state of the project is that Xen with cache coloring is public, is available at the Xilinx entry, is part of the 2020.1 Petalinux release. Upstreaming is still in process. We are about to send the first patch series to the list. Should happen before the end of this year. PV driver support should be coming in the next Petalinux release or soon anyway. So you should be aware that SMMU need to be enabled if you're going to do device assignment of DMA-capable devices to make it work. So SMMU become important, critical. And the conclusions are that, well, Xen is open source, is under the Linux Foundation, type 1 hypervisor, and is a supported part of the Xilinx IoT industrial solution stack. And it's delivered via Yocto and Petalinux. You can just go and look at the Petalinux pre-built if you want to have an easy try of the technology. So Xen cache coloring offers, as you saw from the numbers, much lower execution times under stress, much lower RQ latency under stress. Even more importantly, a greatly improved predictability. So the numbers are way more predictable. There are far fewer, no outliers really, and the rectangle measuring the variance was far, far smaller. So in effect, Xen cache coloring reduces cache interference and enables finally to deploy real-time and non-real-time workloads on the same SoC. All right, now this is time to show you this technology live. So let me explain what I'm going to show you first with the diagram. So I have Xen running, starting DOM 0, and Baremetal application, the blue application at the same time. So this is a DOM 0-less boot. The Baremetal latency application that just does measurements using the TP timer in a loop. And then at some point, we're going to start by hand from DOM 0 a Baremetal memory stress application, something doing memcopy in a loop, basically. And what we're going to see is the Baremetal latency measurements getting far worse when cache coloring is disabled and actually being unaffected when cache coloring is enabled. So I'm going to go and share the screen now. Giulio, can you see the screen?
No, not yet.
Okay. Please let me know when it's available.
Okay.
Hi, Stefano, I see it now.
Yeah,
Thank you.
See it.
Okay, so here is the run with cache coloring disabled. And what you're looking at are the latency measurements results with cache coloring disabled from the Baremetal application. So what I'm going to start now from a separate window is the stress VM. So what we're going to see is the numbers going up from 3,000 to 10,000 to 16,000 and so on. Now this is the kind of degradation that we're talking about. I'm going to reboot the system right now. It's going to take a while. It's going to have to not just reboot the board, but TFTP all the binary one at a time from my laptop as we speak. So it's not the fastest possible setup. But it's the one I work with every day. So it at least is realistic. So here is fetching now. You see the Xen kernel binary and so on. This time I enabled cache coloring. So let's have a look. What did I do to enable cache coloring? So I can show you boot the source. This is the command line. This is the script that I use in U-boot to boot the system. Does a couple of device tree modification, and this is where it adds the command line for Xen. And look at the last few options is setting Xen color to 0, DOM 0 colors from 1 to 6. And this is the DOM 0 less DOM U, the one starting in parallel. And as you can see, there is a color that is color 7 has been set in the configuration. Let's see, here is booting. This is DOM0, and in parallel, you should already see the measurement starting while DOM0 is still booting. DOM0 is up. So what I want to show you, let me start the interference VM, so you're going to see some effects. Wait, sorry, wrong path. Yeah, so it's printing that it's using 10 and 11 as color for the interference VM. There are two VMs running. You see the interference VM called test, and the one without a name, null, is the Baremetal measurement application. Now, if we go up, if you recall, before we were talking about 15,000 or 10,000, while here it's still 3,000 or around 3,000. And the other thing that I want to show you is if you go up at the very early boot information, all the coloring stuff is being printed out helpfully by Xen. So you can see that the weight size is 64K. You can see what the color bit mask is, the maximum number of colors, the size of in terms of memory for each color, the Xen configuration. This is a bit mask, so that would be color 0, and the DOM0 colors. So this is a list, so that is 1 to 6. Then here we have the other domain starting in parallel using color 7. And that is the end of the demo. So I'm going to stop the screen share, go back to the slides. Printed here on the slide the key interesting implementation of both the latency measurement. This is the latency measurement interrupt service routine. And this is the interference loop, in case it wasn't clear how simple is the interference. So that you can repro the setting. Okay, I think I would just want to conclude the webinar, giving you a few links. A few links on where you can find the Xen source code by Xilinx, where you can find information on how to set up Xen on Xilinx boards using Petalinux. Also a reference to the University of Modena and Reggio Emilia in Italy. So they provided key expertise in accomplishing this feature. They've been great partners. As well as donor works that are Xilinx industrial partners and part of the Xilinx Alliance program members. They do Xen engineering services for embedded and Xilinx Zynq MP boards. And we are ready to take questions.
All right, thank you, Giulio and Stefano. So we are running a little long, but we're going to go ahead and answer some of these questions that we've got in the queue now. This will be made available for on-demand viewing later. So if you have to go now, we really appreciate you staying till the end here. So let's go ahead and start with the questions. So Stefano, will Xen eventually be available for installation through the Petalinux configuration?
Good question. We are actually talking about exactly this topic this week at Xilinx internally. Yes, our goal is to make it available through Petalinux config for, well, let me premise that Xen is already available through Petalinux config, right? It's just that you don't have as many pre-built BSP as without Xen. So you can already find Xen pre-built and available on Petalinux config. What I was going to say is enabling of cache coloring that is still a bit manual. And we are talking about how we can find ways to automate that step too.
All right, great. Here's another question. I think this is again for Stefano. Is it correct that this will only work with stage 2 MMU? What about EL3?
That is true. So so Xen uses state 2 in the MMU to set up the memory translation for virtual machines. So this is definitely relying on the state 2 translation in the MMU. So this protection is offered by Xen to the application running on top of Xen, exploiting state 2 translation. So EL3 is, it's in a way is not covered. So the assumption is that EL3 is small and is doing services on, when Xen asks or when other application on top of it ask EL3. So it shouldn't really be an issue from the real-time perspective.
Okay, let's see. Okay, so do we have, here's another question. Is coloring, actually, let's go here. It's as A53 supports both ARINC 64 and 32, would it be possible to use the Xilinx version of Xen with Domo 0? I'm not entirely sure how to.
I think I know the question.
Can you look at question 14 there?
Yeah, I think I know the question. It's a good question, actually. Absolutely. So the answer is yes. So you can run Arch32. So in other words, 32-bit DOMUs on top of a 64-bit Xen. This is definitely supported, and it can give you even lower overhead, because obviously you can get to a lower size using Arch32. So yeah.
Okay, great. Let's see. I think we have one more question we'll get to, and then if we don't get to your question, we'll do our best to follow up offline. Let's see here. Now, is it possible to use this approach with a DMA driver that requires contiguous memory area?
So yes, because we are going to map it contiguously using the SMMU, and that's the reason why I mentioned the SMMU is critical. Because now the SMMU is really important that it's going to do that mapping. So if for any reason you cannot use the SMMU, which should be always possible, but if for any reason you can't, then it's a problem, right? And then your DMA driver is going to have issues. But normally, with the SMMU enabled, it should be fine.
Gotcha. Okay, thank you. All right, I think that is going to do it for us today. I apologize for going over just a little bit. Thank you all for joining us and sticking around to the end of the Q&A. If you would be so kind, there's a little survey on the left-hand side of your console, and that'll pop up when we finish here. If you could fill that out, that'll really help us to continue to bring you the best content that we possibly can. And as a reminder, again, this is available for on-demand viewing. You can find that on xilinx.com/webinars or the link that brought you here today. And you can find a PDF copy of today's slides, as well as some of the links to the support pages that we mentioned in the presentation. Thank you all for joining us, and I hope you all have a wonderful rest of your day.